Hi everyone. Question number 8. Discuss the development of atomic models from Thomson's atomic model to the Bohr atomic model, specifically commenting on the assumptions and failure. Second question is, explain in the experiment that promotes the discovery of electron. First up, J.J. Thomson's atomic model, plum puddings. He discovered electrons but didn't know where they belong. So he imagined the atom as a positive sphere with negative electrons stuck inside, like raisins in a pudding. Problem: later experiments proved there's a tiny, dense center, not a spread out soup. Plus, it couldn't explain why atoms emit light in specific colors. Verdict: nice idea, but it didn't match reality.
The next one is Rutherford's atomic model. The assumptions was atom is mostly empty space. All positive charge and most mass are concentrated in a tiny, dense nucleus. Electrons orbit the nucleus in circular paths like planets around the sun. The failures: first failure is atomic instability. According to classical electromagnetism, orbiting electrons are accelerating, so they should continuously radiate energy and spiral into the nucleus. This doesn't happen in reality, so the model couldn't explain why atoms are stable. The second failure is line spectra. Predicted a continuous emission spectrum, but experiments showed discrete line spectra. Classical physics couldn't explain this quantization. The conclusion was model failed because it couldn't explain atomic stability or discrete spectra.
Then came Niels Bohr. He said electrons can only orbit in fixed energy levels like stars. You are on step 1 or step 2, nowhere in between. Electrons jump between levels to emit or absorb light. This worked perfectly for hydrogen, but failed for every other element. It also couldn't explain finer details like magnetic effects. Verdict: a hero for hydrogen, a zero for everyone else. Alright, so for the second question is, let's go back to how Thomson actually found electrons. He used a glass tube with high voltage and saw a green glow, which is something was traveling. The beam bent toward positive plate, so it was negatively charged. Magnetic fields bent it too, so it was a particle, not wave. The charge to mass ratio was always the same, no matter what gas used. So the conclusion is these tiny negative particles, electrons, are in every single atom. They are universal building blocks.
Question 9. Based on the Millikan's oil drop experiment, a charged oil droplet falls 5 mm in 20 seconds at terminal speed in the absence of an electric field. The relative density of air is 1.35 multiplied by 10 power of negative 3, and that of oil is 0.75 multiplied by 10 power of 3. The viscosity of air is 1.80 multiplied by 10 power of negative 5. So the first one, how many force that exert on the oil drop in the absence of an electric field? The second one, find the radius of the oil drop. And the third one is in 1911, the American physicist Robert A. Millikan report convincing evidence for an accurate determination of the electron's charge, sketched the diagram of Millikan's oil drop experiment, and labeled all its important components. For question 9, part 1, the answer is two forces. Explanation: from lecture notes, the two forces are gravitational force and frictional force. Gravitational force is going to downward, while frictional force is going to upward. At terminal velocity, the drop falls at constant speed, so mg is equal to 6 pi r viscosity velocity. For part 2, first of all, we calculate the velocity by using formula distance over time, and then we know that at terminal velocity, there are no electric fields, so we use formula mg is equal to 6 pi viscosity r multiplied with velocity, and then we derive the equation with mass of the oil drop spherical and effective weight. Next, we plug all the given data from equation into the equation. So the answer we get is 1.66 micrometer. For part 3, this is Millikan's oil drop experiment diagram with labeled components. We have atomizer to produce oil drops, and we have DC power supply to provide voltage P between plates. Reversible voltage allows reversal of electric field direction. Microscope used to observe motion of the drop, and the light is used to illuminate the droplet for viewing. And also we have upper plate and lower plate, and the oil droplet is observed shown between plates.
Okay, for question 10, Rutherford scattering formula describes the number of scattered particles detected at a given angle. The counting rate number of counts per second is proportional to Z atomic number of the target foil over Ek kinetic energy of the incident particle squared times by sine to the power of 4 of half the angle. Okay, for part 1, when the detector moves to a larger scattering angle, the counting rate decreases. This is because Rutherford's scattering formula tells us that the number of scattered particles is inversely proportional to the sine to the power of 4 of half the angle. As the angle increases, the value of sine half angle also increases, making the denominator larger. As a result, the number of counts per second detected dropped significantly, so my answer is decrease.
Okay, for part 2, when we replace alpha particles with protons, the counting rate decreases. An alpha particle has a charge of positive 2 electron, while a proton has a charge of positive 1 electron. In Rutherford scattering, the counting rate is proportional to the square of the product of the charge of the projectile and the target. If we keep the kinetic energy the same, replacing an alpha particle with a proton reduces the effective charge factor from 2 to 1. This means the new rate is only 1/4 of the original rate. Therefore, the counting rate decreases.
For part 3, when the silver foil with atomic number 47 is replaced with a gold foil of atomic number 79, the counting rate increases. According to Rutherford's formula, the counting rate is proportional to the square of the atomic number of the target nucleus. Since gold has a higher Z value than silver, the ratio of the new weight to the old weight is 79 squared divided by 47 squared, which gives approximately 2.82. This means the detector will count almost 3 times more scattered particles, so the counting rate increases.